Hi, everybody. So we're getting to the end of the day, and I hope you enjoyed it so far. First of all, I would like to thank the organizers for extending me an invitation to be here today to present. I feel very honored to be in such a wonderful company. And I was humbled by, yeah, okay, I will try. My mic, oh, sorry, yeah, let me try to fix that. Just a second, should be fine. Is it better? Yes. Wonderful. Okay, so I was really humbled by all the presentations today and by how, the presentations look like, super polished. So mine is not super polished, but I'll try to keep it interesting nevertheless. All right, so I'm part of the AI automation group at IBM Research. We focus mostly or exclusively nowadays on automated visual inspection, and anomaly detection is one use case that I wanted to talk to you about today. But if you see the pictures that we're showing here, we have quite a few use cases where automated visual inspection helps, right, to find defects, to classify defects, to segment images, and then also to take decisions, for example, what needs to be done in terms of maintenance, repairs, operations, and so on. So I'll start with a little example. Okay, this is a pin board. Okay, so it comes from one of our products, is System Z. It's silicon pins. Can you tell me how many anomalies do you see on this image? Would you like to take a wild guess? 10. Another guess? Okay. Actually, it's 35. Okay? So some of these defects are actually so small that you need to really zoom into the image to actually see something. And so for your benefit and also my benefit, I just put some bounding boxes around the defects, and it's still not clear where these defects are. So let me just show you the mask. Right? So if you were to segment the image, annotate all of your defects, these are the defects that you get. Some of these are bent pins, some of these are missing pins, some of these are actually hairs. We don't know how they got there, but they got there, right? And they are still considered to be defects, and we want to be able to identify them, to localize them properly. And some of these anomalies are actually a few pixels wide, 1, 2, 3 pixels, in an image that goes over 20 megapixels, right? So we're talking really about high-resolution images that we have to deal with. So, okay, is this problem not solved? Because anomaly detection has been roaming the Earth since the dinosaurs, right? So everybody has done some work in anomaly detection, or a lot of people have done this. So in our product, right, which is maximum visual inspection, to which we try to contribute, we already have anomaly detection inside. And it doesn't work. Why doesn't it work? So we have, I won't name the model because I don't want to offend anybody. It's from a competing company. But this model we have adopted, we have put into the product. And actually, when you try it on public benchmarks, it works great. You cannot beat it. You have almost 100% accuracy in localizing the defects because all you have is very simple things. You have very small images, low resolution, big defects. So it's a much, much easier problem to solve. So the problem that we are facing is that we work with customers that give us high-resolution images. They give us a handful of samples because they don't bother to collect more, or they cannot collect more, right? And then these images are not really taken under perfect conditions. You're never going to get an image on a uniform background. Never. You're going to get an image that has been taken with different lighting conditions, maybe a bit tilted, maybe a bit zoomed in, some of them zoomed out, right? So there is not a integrated process here to take images properly. And what the current model is doing, right, it uses fixed thresholding. So what that means is we return you a very nice score map or a heat map, and then you as the user, as the consumer, you need to decide what is that perfect threshold that will maximize your true positive rate and minimize your false positive rate. Good luck with that. It might be 0.5, but it might be 0.6713 and then 10 other decimals at the end, right? So what I put here, and you can see I'm a researcher, so I put numbers to the problem, right? When we actually looked at some of real use cases scenarios, so proper data sets, real-world scenarios that we get from our customers, these are the values you get. This is the evaluation of the current model. You have a 0.8 IOU. That's not very high, I would say, on a range that goes from 0 to 1. There's quite a lot of improvement, right? And the same goes for another use case that I will show later on, which is a much easier use case in which we collaborate with Ford to find defects on their oil filters underneath the hood of the car, right? But you can see here that our true positive rate is quite low. The false positives are quite high, and we miss quite a lot of defects. And actually, sadly, on the silicone pins that I was showing before, the current model that IBM has in Maximo will just generate, huge bounding boxes, a lot of these big areas that are actually false positives. And if you're lucky, you might get some of these defects, if you're lucky, if the defects are big enough, right? So what we're trying to do is actually something else. So we came up with an idea, and this idea seems to work much better, which is why we are now replacing the current anomaly detection model in the product, and we're offering this to the customers. And actually, we use a two-step approach, if you want. We couple visual prompting. Maybe you're familiar with it. It's the new cool kit for computer vision. Everybody's trying to do visual prompting in some way. And then we couple it with anomaly detection. So basically, what we are doing is we use visual prompting. We give you some images if you are a user, if you're a customer. And please scribble for us what is the area that you're interested in. And hopefully, we have a good enough model that we will generate really good masks around your area of interest, in this case, the pinboard. Yeah? And this is the only thing that will go into the anomaly detection model. We don't want to pollute the model with variations in the background. We also want to be able to exclude parts from that image that are not relevant. So to give you an example, and let me try to find a laser here. So here you see the middle of the pinboard. Actually, the pinboard is composed out of two halves, and we don't want to have the middle included in the mask. So our visual prompting capability actually contains also the ability to offer negative prompts. So as a user, I can tell you, this is a negative prompt. I don't want you to include that in the final mask, right? And we can generate these really perfect masks. And then we feed these into the anomaly detection, and voila. We get a very clean heat map, and we are able to localize the defects. Not perfectly. Some cases are, of course, easier, and some cases are harder. But basically, this is what you would get. So the same goes for the oil filter here, right? This is the Ford use case that I've mentioned before. We localize the object. You can see that actually the object that we're interested in counts for what? 5–10% of the image. Everything else is irrelevant for this particular use case. We can throw it away, which we do. And we only feed the oil filter to the anomaly detection, and then we get a score map that actually looks like what we want to see. We are seeing that we are localizing the defect properly. So how do we do this? I'll just go very quickly through some of these things, right? What the customer would do now in MVI, you would upload your new training data set, and then to enable visual prompting, we have a capability that we have built out of our lab here across the street, right? We have VP Lab, so this is the visual prompting lab. You would send us like 1 or 2 images, reference images. You would scribble on them, points or lines or curves, doesn't really matter, as long as you localize what you want. And then we will give you back a nice wrapper. And that wrapper is your model, and the visual prompting model is actually quite complex, right? And then the area of interest masks for those reference images, and we propagate that further through the entire data set. And this happens actually quite quickly. So it's not a huge effort for us to do. We use these masks to remove the background, and then we run the anomaly detection. And so the anomaly detection is another beast. I'm not going to go into the specifics of the model. I will maybe hint to some of the elements here. But what works very well for us is we need to make decisions whether you can feed the entire image, even like this, even when we have isolated the area of interest. Do we want to feed it into the model? Can we do that? Is our backbone able to take such an image, or do we have to downscale and tile? And these are decisions that we're making automatically depending on the size of the defects that we are expecting and depending on the resolution of the image. Then we generate the score maps, and then we save the trained model. And once we have saved the trained model, we can go to inference. And as a customer, you don't really need to do a lot. You just need to take your visual prompting wrapper, You need to run it through your test data set again, and then you're just going to run your anomaly detection model. You're going to generate the score maps, which is where most anomaly detection models stop, right? Nobody else goes beyond this point. Everything else is manual from this point onwards, so we automate as well this part. We find you the optimal threshold, and we localize the anomaly, and what you're going to get is a mask and a nice bounding box around the defect. And this is all available now in the Maximo Visual Inspection products. So we have successfully, replaced a pipeline that was not working before with something that is actually giving better results. So what does it mean to give better results? So for the pinboard use case that I was showing before, we get images that are quite big. Like I said, we are about 20 to 24 megapixels in resolution, and the defect types that we're expecting are small and many. What do you need to do for pinboards to make it work? So first of all, we work in a low data regime. This is very important to mention because anomaly detection is usually, in order to make it work, you need to train it on thousands of samples. We have a good number. We have 146. On some use cases, we have 50, and that's all you can learn from, right? We annotate one sample, so we ask the user to scribble on one image and one image only. We get these perfect masks, and we get the perfect masks with a lot of hard work behind the visual prompting model, of course. And then we are running, the anomaly detection. And why I'm showing here why visual prompting is so important is because without visual prompting, we actually lose quite a lot of defects. We also generate more false positives, which is this column here, the second one. And then with visual prompting, we're actually almost flipping the results. So we're very, very good in comparison. And do consider that these defects are extremely small. Now, when you look at the IOU, you might say, oh, OK, well, you go from 0.08 to 0.5. So you still have some space to improve. Most of our customers that we work with, they care about the hit ratio. Are you finding me? Are you localizing at least in the region of the defect? It's OK if your bounding box is not fitting perfectly over our ground truth as long as you catch the defect. So our true measures here when we present this to customers are true positives and false positives and missed defects. Right? That's what they care about. The IOU, they don't really understand. So you would always need to explain what intersection over union means. All right? And the same goes for the oil filter. So here we actually have even less images, 86. These images, they look exactly like this. So whoever took these images did a wonderful job, because some of them are extremely blurry, right? And we work with images taken under, like I said, varying conditions. We don't have a standardized process to take these images, not as you would in a proper process, unfortunately, but we still actually manage to deliver pretty good results. So we actually managed to reduce the false positive rate by 29x, which is quite impressive, right? So we give them perfect results, and they're very, very happy. Now, this is actually I think the last slide I have in my presentation, but I did want to mention that without going into the specifics of the methods behind, right? One of the key challenges that we have with customers is that they want perfect results, but they want perfect results in a very, very short amount of time. So if they could run this on the fly, it would be great. And if they could use like a very, very old GPU, or even better, just a CPU, it would be even better, right? So it's always a matter of managing expectations, right? And it's also an opportunity for us to think outside the box. So our current model, for example, the entire pipeline involves SAM as a backbone, Dino V2. We have visual transformers. We have masked autoencoders, feature pyramid networks. I mean, we throw everything at it, right? So we do everything that is on the market right now in computer vision to get these results. And of course, the moment you tell them, oh, on a T4, which is from the dinosaur era, you will run this in 12 hours, there is silence, right? They expect that it should train in 5 minutes. It's never going to train in 5 minutes. But what we are doing right now, we're investing a lot of effort into making the model, the whole entire pipeline, not only the anomaly detection, but also the visual prompting. We want to make it faster, and we want to make it lighter. And there are different ways to do this. And if you've looked into these things, you know about model compression, you know about quantization, you know about distillation, right? You know about token merging. So we are using all of these techniques together at the moment. And we are getting an improvement of about 90%. So we are able to train 9 times faster to get the model with the same performance, right? And we are using about 30% of the GPU, which I would say, it's actually quite acceptable, where their absolute cap for a GPU is 16 gigabytes. So we're talking about, very, very, very poor resources from our customer side. But it's an opportunity, like I said, for us to first of all, actually drive research based on real use cases, not just focus, for example, on getting some numbers on public benchmarks, publish, and then move to the next problem, but actually see that when you apply them on real data, you will encounter problems that you didn't consider before. You didn't think about them, so you need to go back to the whiteboard, and you need to go back to rethinking the problem and how you can solve things. And actually, we live in a world where, fortunately, AI gives us a lot of possibilities to move forward, right? So we have so many alternatives to use, and so that's what we are taking advantage of here. In the interest of time, I think I'll stop here, and thank you very much for your attention.
That was really very interesting. Thank you, Anna. So the first question I'd like to ask, part of which you already answered, is how long it takes to train these systems and to make an inference on them. But as a complementary question, I would ask, how do you see the response from the customer side now that you've made all these improvements? And what sort of scale do they expect? How many images, say, an hour, a day, a year, would they expect to feed into the system?
A very good question, thank you. So first of all, the response has been great. They're very happy to be able to continue to use their ancient hardware to run our models. We were actually hoping to be able to convince them to upgrade, but we couldn't convince them. So it just drove us to work more and to solve the problem, which is great. Now, in terms of use cases, what they envision is, we work a lot with manufacturing use cases. So you have an assembly line. The assembly line is constantly moving, right? You're assembling cars. It constantly moves. It never stops. And the way, for example, that Ford works, which is the easiest use case we have, the moment that you have generated a false positive, they stop the assembly line. And then they go and they inspect whether to see, is this really a mistake of the model? And it loses a lot of time until they restart the production line. So it is imperative, right, to be able to run inference really fast, almost near real time. But we are at 8 milliseconds for the oil filter, so I think we're good. On an edge device, right?
That's great. So these edge devices, I presume, are also quite ancient.
Yes. But, I work for IBM. We are old school. We like challenges from the dinosaur era.
I'd like to open it up to the audience if you have questions.
Hi. I thought it was a brilliant talk. Thanks so much. I was wondering, so I work a lot in the ML for education space, and there we also have this low data problem or small data problem. And a lot of what we're doing in the lab is working with data augmentation techniques. And I was wondering whether you considered exploring it for the problem.
We did, but it was just slowing down the training, right? So then we went the route of fine-tuning, for example. So for example, what we are doing for visual prompting, we fine-tune, and we also have contrastive learning and fine-tuning in the anomaly detection. So we don't need to augment our data set, we just fine-tune on it and get better results.
One more question from the audience before we move on. All right. No? Thank you very much, Dr. GIURGIU. It was really a very interesting talk.